Hi. Yeah, I was going to say now for something completely different, but that's clear already. So thank you, Aaron, and thank you for inviting me to speak. Um, I so Aaron said yesterday, most of you who were around, that he was Partha's most applied student, um, and so applications are an area of his work that maybe not everyone familiar with. I think people are even less familiar with the language evolution aspect of his work. So I'm Partha's most linguistic student, I think you could say. And in part because of that, I wanted to just spend a minute going over some of his work on just the scope of his work on language learning and evolution. So Natalia Komarova talked about some of this the other day, and Partha often, yeah, I think he was sort of amused sometimes. He often talked about language evolution and linguistics and so on. That he led multiple lives. I think many of you know, and he described this story where a very well-known machine learning person he knew that he was talking to for a while, they started talking about language, and then eventually the subject came out, and he saw that Partha seemed unusually knowledgeable about this, and then he said, yeah, I actually have a book on it, and this guy was just blown away. And he said, in general, people didn't know about this language evolution work. Those of us who dealt with him on the language side, I think, knew that he obviously was a big person in machine learning, but we didn't actually understand that much of it necessarily. So I think it's just remarkable because he managed to have such a body of work and an impact in really diverse areas. I just wanted to briefly say, just to splash all the references here and say there was a huge amount of work that Partha did on language evolution and change and learning. A lot of the early work was with Bob Berwick. Some of the medium term to later work was with Natalia Komarova and Martin Novak. And then some work published after this book was with Dinesh Surendran, and then with very late on with me. So this is the book. I just wanted to say there's two chapters on language learning, which is various properties of language learners that have been proposed in the linguistic literature. He actually worked out the formal properties of them and their convergence properties and so on. To my knowledge, almost no one else has done that. 6 chapters on language change. There's a smattering of work around on mathematical models of language change, but really nothing like this. And there's just so many ideas in there that have not been picked up on or expanded yet, but are just really fertile ground for future work. And finally, work on the origin of language, which you heard more about the other day. I'm going to talk mostly about the language change side, and in particular our paper that or two that we wrote on it, which is independent of the book. So again, because people here are probably less familiar with this work, I wanted to give some sense of the broad motivation for this side of Partha's work, and this direction of work in general. He always used to say that for him, this had to do with learning fundamentally. I mean, like I think somebody said on the first day, 2 words that really encapsulate a lot of his research are language and learning, right? So a lot of things had to do with various aspects of human speech and language, how you learn them, how you learn given limited data. And the tension that he saw was that language learning in children is excellent. So children more or less acquire the language of their parent perfectly. I mean, we know there are slight differences, but the amount of time in non-pathological cases, every child succeeds at this. Every child does it almost perfectly, and children sound more or less like their communities. And when I say more or less, I mean within a very small epsilon, right? At the same time, we know that language change is constant, right? Anyone who's ever tried to read Shakespeare or even worse, Old English knows that by the time you get back to Old English, it's a completely different language. And this is true for any language. So the tension that he saw was that people before him have seen, but did not put so crisply in the mathematical framework, was that there's a tension here, right? If all learning was perfect, you would never get change. But we know that because change is constant, there must be some way that learning leads to change. What is the relationship between those two? So why does language ever change? And in particular, what determines the structure of which changes occur and which ones don't? Changes that do happen are not at all random. They tend to happen in very regular ways that we see repeat themselves a lot, and many changes that you could conceive of tend to not happen. So in this perspective, the really broad perspective that I'll be sketching out in more detail in the project we looked at, language evolution is the population level outcome of learning by individuals. That seems like, a a very intuitive statement, and it is, but it was again Partha who put it so crisply and in a framework where you can use it to test theories. So in order to reason about this relationship between individual learning and population dynamics, you need a mathematical framework because the map between those two is far from clear. So as I hope to illustrate a little bit in this talk, there's been very long interest in linguistics and among many people in saying this is why language changes in a particular way. It's because children learn less accuracy or because people want to sound like each other and so on. But those are all statements about how individuals learn things. And when we talk about language change, it's something that happens at the level of a population. Partha really fleshed out that that map is non-trivial and that it has some really interesting and surprising properties when you look into this framework. He often made the analogy, at least in conversation with me, and I think it's in the book as well to some extent, with biology. People have brought up here a lot. I think that Partha was very optimistic about the way things could go in any field while being realistic about it. And he suggested I think in a sort of third whimsical way, that historical linguistics and the evolution of language was sort of now where evolutionary biology was in the 30s, in that there was a theory of natural selection and there was a theory of population, more like in the 20s. There was a theory of natural selection but there were a number of basic facts there was a theory of natural selection, there was a theory of genetics. I don't know that much about biological evolution, but how to reconcile them was not at all clear. And in his view, and I've seen this borne out in more reading on the topic, a really crucial role in bringing those two together and leading to the modern evolutionary synthesis that we all learn in biology class now was Fisher's development of a mathematical framework for population genetics. And that really allowed people to reconcile a lot of things in those two directions of work and see that actually it played out very naturally. His point was that you really needed that mathematical framework in order to reason about how assumptions about not learning now, but reproduction and passing on of genes played out at a population biology level. And he hoped that this program and computational work on change more generally would sort of lead us in that direction. So what I'm going to be talking about today is a combination of this approach that he had with a case from a relatively detailed case of language change, so data from that case. I just have a quote here from the end of the book, and I know he did think that empirical data was important, I think in all aspects of his work. It was often sort of, to some extent, theory first, but then it's extremely important that there be data. If you're from MIT, you'll find it funny that he used to say there was too much mind and not enough hand, because the model was mens in manus. And in particular, I'm going to be talking about the work that's reported in an ACL paper and in my math. So there's been a lot of computational interest in language evolution and change, especially over the past 15 years, really picking up around when Partha and Bob Berwick wrote their sort of seminal article on language change. It's been in a number of languages. And the broad motivation is the questions that I sketched before, which are, once you start to think about it in this framework they did, these are very computational questions. Why does language in a population ever change at all? And given that it does, why does it change in the particular ways that it does? So the central mathematical question here is, what is the relationship between the population dynamics you observe and the behavior of the individual agent, so learning by individuals? The approach we took in this project combines longitudinal data from a particular case with mathematical modeling. And the sort of schematic approach is that you have three ingredients here. You have hypotheses about why you think some change happened. And you have, these can be based either in learning, and they can be based in assumptions about the population, so maybe how much people want to imitate each other and so on. You also have data on that change that you observe. This data gives you empirical observations about what the dynamics looked like. The more detailed, the better, so that your models aren't doomed to success. Your hypotheses of how people learn, iterated over time, will give you what the predicted population dynamics are for different models. And you try to match these up in a fashion similar to other applications of mathematical reasoning. And you combine these you compare these using the language dynamical systems. So note that I didn't match the data directly with the dynamics that I observe. I say the data will show us certain properties, those properties such as bifurcations are things that we'll try to see in the dynamics. It's a high-level idea. So let me just jump right in. data that we looked at in particular is so-called noun-verb pairs in English. So these are things like the word fracture. You pronounce both the noun and the verb with initial stress, fracture, fracture. With words like contest, you, at this moment in American English at least, you pronounce the noun with initial stress and the verb with final stress. So you say it was a contested election, but we had a contest. And there's a bunch of them that you pronounce with final stress, so words like police or review for both the noun and the verb. There's a bunch of words that fall into each category. Never a so-called 2-1 word, right? So a word that's like, if we said gabor was a noun and a verb, then you would never have a word that said like, I have a gabor, but I gabored for lunch. So the overall pattern that you see in this data over time is stability within these things. So words that used to have this stress pattern in 1600 or 1700 overall maintain it over time. Words that had a different stress pattern tend to maintain it. But you do see a subset of these words in which there is variation and change over time. So the word contest used to be pronounced for the noun and the verb. And the question is, what are the dynamics and why did they play out the way they did? So the data set we've used is to look for these words in 62 British dictionaries. Up to 1800, it's filled in by some prior work. The rest of them were done looking at a lot of dictionaries by myself. You end up with 8,000 entries or so, which is a pretty sparse matrix because a lot of words were not in use for all time. So this is what the sort of data we have looks like at a schematic level. Yeah. Yeah, there were. Yeah. So, well, in particular, there were word lists for foreign learners that used stress. But the dictionaries themselves are fairly sparse up to about 1700. So that's where you start getting really, really good, good dictionaries from the purpose of stress. So one nice thing about, if anyone's interested in this, one nice thing about looking at things like stress that are very salient about a language but don't involve actual segmental transcription is that they're often remarked very, very far back in the historical record because they seem to stand out enough. So the same is true for Russian dictionaries back to about 1750, I think. So if you take the moving average basically of noun and verb stresses over time, you get plots like this, right? So the blue line says this word combat was always pronounced as combat, but the verb combat changed over time so that it became suddenly around 1775 combat for the verb. And this is the kind of pattern, if you know this side of Partha's work at all, that he was just fascinated by. He wanted to know, how was it that you got up to 1750 and you would sound crazy if you said that verb, the same way I would sound funny if I said the opposite now. And then 30 years later, the opposite situation. He was more interested in cases previous to this work where you saw it for things like word order, where it's even more striking. But this is another example, right, where you see some variation around the edge. So there were some time periods where people seemed okay with using both terms, but they more or less stayed stable over time. So we have these patterns for 150 words. And to summarize what you see, the really common changes are from 2-2 to 1-2. So things like words like concert became concert for the noun, but stayed in their form as the verb. This one's less common, but it happens. So things like dictate used to be dictate for the noun and the verb. At least in British English now, it's dictate. These are less common. It's change away from this pattern. So the thing to notice here is that there's a lot of change to this pattern, a lot of change, relatively little change from this pattern, and that this one is the most common change. So there seems to be an effect of frequency, and that the lower frequency words change more easily. And it seems to be the case in some empirical data that it's falling frequency which triggers change. That's a little more speculative, and I'll come back to that. Really importantly, especially given previous work on modeling language change, there's a lot of variation going on. So variation here is endemic. If you have a word, and even though you probably think you don't, if I measure you over a period of time, you actually, for the subset of words that are in variation in the population currently, like research, people will say both research and research in American English. Many, many people say both, just at different frequencies, right? So you see that at a given point in time. You also see stable variation in one word over time. So something like discount for the verb form has been both discount and discount, although it's a rare verb for a few hundred years. So it's with the diachronic perspective that you're able to get these broad patterns and say, where the hell do they come from? So there have been sources of this kind of change proposed in the literature. So one major source is so-called mistransmission. So this is the kind of thing that's suggested for a lot of sound changes, which is that perceptually you're more liable to mishear things one way than another. So the dominant stress pattern in English is that nouns have initial stress. Something like 90% of words in English, 80 or 90% have initial stress. So if you hear something like research, in experiments, if I do that with like the word like Gabor again, you have some probability of mishearing it with initial stress and reporting that, but you have a much smaller probability, nearer to 0, of doing the opposite error. Another broad kind of explanation is analogy, which is, and your sort of the influence of your lexicon, which is, as I said, nouns in English are overwhelmingly initial stress. Verbs, the pattern is less categorical, but they are very tilted towards having final stress. So when you hear a new word and you have to learn a novel word, your perception of it tends to be biased, or you could think that you have influence of all the words that are near it. And you see this effects of this asymmetry very early in acquisition in children, which is crucial here, right? So the mathematical framework uses discrete dynamical systems. I'll sort of go through this quickly because it's, for the original audience, this needed, I mean, sometimes this needs more explanation, but this is a group where I think this is fairly baby stuff. So a discrete dynamical system is just a system that evolved in discrete time. It was Niyogi and Berwick who ported them to linguistic populations. If you're familiar with population biology, this is the kind of system that's used there a lot. It's also used in chemical reactions, so on. You just have some arbitrary map of a parameter that evolves in discrete time, and you're trying to determine the properties of that map f. And because in general, you can't actually determine explicitly what the moment-to-moment behavior of this map is, the dynamical system's viewpoint is to look in the limit and see what happens. So one crucial concept here is that of fixed point, right? So in the limit, at least for the dynamical systems that we'll be looking at here, you get to a fixed point, right? You get to some stable situation, which is either unstable or stable, right? So it's a pencil on its tip or it's a pendulum either at the top or a pendulum at the bottom, right? You can also get things like limit cycles and so on, but one really nice finding of Partha was that these tend not to occur at all so the sort of nasty things that you learn about in a dynamical systems class, or the nice things depending on your perspective, like limit cycles and chaos, don't occur for the kind of systems we're looking here, and they showed that formally. The really crucial thing you're going to find is bifurcation. So as some system parameters vary, you get a change in the number or stability of fixed points, right? So this is something like Natalia Komarova said the other day, just with water, as you vary the temperature, it goes from the solid state being, the stable state being solid to one where it's, one where it's liquid to one where it's steam. And this in general happens in a more complex way. You can also get multiple points emerging. So in this viewpoint, change away from some fixed point corresponds to a bifurcation where it loses stability. It's sort of crucial for this viewpoint of language change. So the goal of a dynamical systems analysis of this map is to find the fixed points and the stabilities, and given, if I tell you the parameters by which the system can vary, to determine the bifurcation structures. So it's the same thing you do in a class on dynamical systems, but for a particular applied case. And in the language setting, what this the bifurcation structure tells you what the possible and impossible changes are. So there's a very nice correspondence between this thing of linguistic interest, which is to know what are the possible changes, and this mathematical property. So from this perspective, we can conceptualize the observed from the data as desired properties for a dynamical system, right? So we'd like each of those things to be a stable state, at least a possible stable state. So each of those should be a fixed point under some system parameters. We'd like it to be possible to get variation between them. So have a stable state that involves that's at 1.5, not 2, right? We would like this to never happen because we never see to see the bifurcation structure reflect kinds of changes that we see, and we would like ideally to see a frequency dependence look like we saw. So frequency will be a system parameter, right? Frequency of the word, and as it drops, we'd like to see a change initiated to 1 to this pattern. So we want we can test models of why the change happens against which property we give. This is an outline of what I'm going to tell you about the models. We're going to consider 6 models of learning here, but I'll just say briefly that we did consider a much broader range of models that are written down in my thesis, and that we plan to write up. But I think, like many of you here, the work got cut off by his illness. But I'm going to describe a sort of set of 6 here that I think neatly encapsulate the program. So this is a diagram of what a learner looks like in this model. Every learner gets the same number of verbs and the same number of noun examples. Every verb or noun example is either initial stress or final stress. Based on that, they have an algorithm that tells them the probability with which they should pronounce verbs as final stress in their own production, and the probability which they should pronounce nouns as final stress. Every such learner gets input from the previous generation, right? So what I'm trying to show you here is that these are the probabilities. These learners then produce a bunch of data. This one draws IID from the past generation with equal probability from each speaker. So these are all simplifications of social structure and so on. And then we do that for each learner. And you iterate that over time and see what the asymptotic dynamics are. So the assumptions here are that each generation is infinite. There's perfect mixing, meaning that I draw evenly from each person in the past generation, and that these are fixed values for everyone. Both in our work and in work reported in the book, there was a lot of interest in relaxing these assumptions and seeing what difference it made. For example, if instead of having these be fixed, you let them be drawn from a distribution, which is more realistic, and so on. But he had a really good knack for figuring out what the assumptions were that you could make that were going to make things qualitatively different, and what the things were that sort of fuzzied it around the edges. So this assumption about each generation being infinite is crucial if you want to actually determine dynamics. Otherwise, it becomes a stochastic process. On the other hand, we know in population biology that once the population size is beyond a relatively small number, it actually looks like a dynamical system. It's just way harder to analyze. You end up with a stochastic process that just ends up in one state forever, and then another, for some notion of forever. So the notation I'm going to use here is that alpha t stands for the ensemble average of the learned parameter at time t. Beta t stands for the ensemble average of that learned parameter at time t. And we are looking at how those things evolve over time. So this is the dynamical system. Is what is the average value of the stress for this word over time? Nouns and verbs. What is the average probability if I were to ask everyone in this room right now how to pronounce research as a noun or a verb? Those would be these values. So from hypothesized sources of change in the literature, we have 2 dimensions of assumptions about the learners we can hypothesize. They can either be liable to mishear things or not in that sort of fashion that I described earlier. And they can also have some effect of what we're calling here analogy or not, right? So you have to operationalize this notion in some form. And I'll describe several notions of that. So notice also that these are, and this is a point that Partha was very about this work in general. These are 2 different these are 2 different ways of thinking about something that basically will give you, at least intuitively, gives you a similar outcome. They're both ways of saying, I like forms that have initial stress. I don't like ones that have final stress. They just have different reasons for it. But you'll see that they lead to extremely different dynamics when iterated over time. And that was a big motivation for this kind of approach. So the first model is one where you just have simple mistransmission, right? So when I say a noun with final stress, you have some probability of mishearing it with initial stress. You have some probability of hearing it correctly. And as a simplification, I say that when it's produced with initial stress, you have no probability of hearing it with final stress. In reality, this is just a very small number, right? But this is a simplification you make here. And this means that as a learner at time t, your probability for any given example of hearing something with final stress and initial stress get a little more complicated than they would have been before, right? So I can either hear something as initial stress because it was mispronounced or because it was pronounced correctly. But the same is not true for the final stress verb. So we have this sort of asymmetry in the system. So each learner now draws, by drawing N1 examples, they draw a binomial distribution from the last generation. And the simple algorithm we use here is just that you probability match. So I hear K1 of them as being final stress, and I just set that over the total number I heard. That's my probability. It's very simple. And what you end up getting here, if you do the evolution equations out, it's very simple. This is what you get. Like Vikas said, Partha liked these examples that were very simple but got you some interesting behavior. You get a unique fixed point. This point corresponds to everybody using the 1-2 form, right, which is the thing that you most commonly see change to. Okay, so that's at least qualitatively interesting, but it doesn't show most properties that we were looking for, right? So it's never possible that all initial stress is stable, and it's never possible that all final stress is stable. It's not possible that you get variation and so on, right? There's never change. So that can't be the whole story. So in the second model, how many fingers was that? Okay. So in the second kind of model, you have coupling instead by some sort of constraint. So you will say that I basically know, because of my knowledge of the language, that I have to set that value lower than that one. So nouns have earlier stresses than verbs, basically. One way to do that is just to say that if I get data that doesn't satisfy that constraint, then I choose the closest point in alpha beta space that does. If you do out that evolution equation, you end up getting basically that every point is stable where you have some variation in the noun or the verb, but not the opposite, right? So that's nice, and you change towards that point if you're not there. That gives us some of the patterns we were looking for, but it doesn't give us the way that change happens, right? The way that we see change happening historically is not along this axis, which is what's good. It's along these axes. That can't be quite right either, but it's better. If we do that same thing now, the same kind of learners, but we allow them to have mistransmission, then I'll just tell you that now we get all the desired properties except, sorry, we don't get any of the desired properties, because basically you now end up getting a unique fixed point again. So you're back to where you started. Finally, this is a setting where this is another notion of what it means to have analogy or coupling, is that you basically have a prior probability for each of these patterns, right? Because of your knowledge of the language so far. So remember, these noun-verb pairs, right, tend to be, at least one of them, one member of the pair tends to be fairly rare, so it's reasonable to think that these are acquired somewhat late in acquisition, and you already have some knowledge of the aggregate statistics of your language. Given some prior probabilities of those patterns, we can sort of cheat and say, well, somehow you've inferred that you can't have something that is noun, final, verb, initial, noun with a final stress, verb with an initial stress. And that's not so crazy if you look at the developmental evidence about this. Very early on, kids are very uncomfortable about this. So if you then basically make your hypotheses based on the empirical probabilities that you heard. So make a hypothesis for each kind of grammar, right? A 1-1 grammar, a 1-2 grammar, and then weight them by these prior probabilities. This is what you'll get. And you end up getting a relatively complex structure of fixed points and bifurcations, but the upshot is that the bifurcations correspond to exactly the kinds of possible changes that you observe in the data. The only thing that's missing is that change to 1-2 is not frequently dependent, right? But we're getting much better here in terms of matching models to data. And also stable variation, right? Because here we're predicting that each grammar is uniquely determined. So if you wrap mistransmission into that mix, then you more or less get everything you're looking for. You get that same picture, except now you can have stable variation. So I have a bunch of checks here. This is just to say that this is a comparison of the different types of model. And I know that the kind of thing Partha often like to emphasize about this kind of figure was that each of these models sounded plausible at the outset as a reason why this change happened. But iterated over time among a population of learners, they lead to extremely different outcomes. I'm not sure how that might sound sort of duh to people here, but linguistically, it's not at all a sort of widely recognized. Amount of time, I'm not going to say much about the kind of observations we can make, except that there's a relatively complex interplay of learning and population level structure. To make a connection to the literature in particular, it's interesting that by far the most commonly proposed type source of change is something like this. You just mishear things. You have some probability of mishearing stuff. The question Partha always asked about this was, well, if it's so hard to hear, if there's some asymmetric probability of mishearing this thing, why is it still around in some languages? You know, if final stress is so disfavored in English for nouns, then why do we have it for some nouns? That's kind of what you see playing out in these models. If you just have this factor, it becomes impossible to maintain final stress on nouns. And so it's just, interesting looking at the literature because, again, that is the most commonly proposed type of things. It suggests that we'll gain a lot of insight by wrapping them into these type of population models and seeing how things have to be constrained to get them to work out to give the observed dynamics. To make a discussion, this one contribution of this data set is that it works with real world data. So it works with language change data. It's fairly complex. It could be much more so. And there's relatively little work of this sort. If you look at there's almost 2,000 entries now in work on language evolution and change from a computational perspective. Very little of it deals with data. So that's interesting. And we like this point a lot, that by using more complex data, what you're doing is constraining the desired behavior of your model. So you're not saying, I just want to see something like an S-shaped curve or so on. You're actually sort of tying your hands a lot. You're saying, all of my models will be wrong. I just want to find the one that's most useful. All models have some desired properties. Not all of them have the ones you expect. And of course, though, there's a lot of limitations here. We've only considered schematic properties. And as Vikas said, in future work, you always wrap in the things you may never do. By using a landscape, in quotes, of simple models, of relatively simple models, we're able to reason about how assumptions about individuals affect the population dynamics. As I said, we have a more complex landscape that just didn't make it into this paper. This is a useful exercise because of this non-trivial map. This forms sort of a complementary perspective with a lot of computational work on language change and indeed language evolution, where you use very few models, but at least in the better work in this area, the models are able to be much more complex, right? So you're able to wrap in much more realistic assumptions about how people learn and use language and determine those carefully. And this is, as in all of biological systems work, this is always a trade-off between increased realism and the sort of amount of knowledge you're able to get into why what you're doing works, and actual realism in what the model is. And that is it. Thank you.
For one question.
Okay.
Hi. Yeah, I'm looking at that assumption that the mistransmission model is out because of the fixed point. And I wondered if you were familiar with by Baxter's slide on how fast you reach this fixed point. So they were looking at some language evolution models for New Zealand English, and basically argued that the basic model did not converge fast enough to the observed behavior, which might so that you had to make some complications, which I won't go into here. So, for example, what if you do have the kind of mistransmission of the population is not fairly mixing, and you're injecting borrowings from French pretty fast compared to how the regularization occurs. Garage, ballet, and all of those words are being borrowed in at the same time that you're regularizing others. And of course, I'm partly inspired to suggest this by the recent article I had, which suggested that most words are not known by the whole population. Most words are to some extent concentrated.
Yeah. No, and certainly in the time period we're looking at, right, a lot of these words only start out that way. Yeah, it's not a model that we looked at, but it's certainly one that's very realistic. I mean, there's been a lot of debate in the philological literature here, in the linguistic literature, about how much of a role French borrowings were playing in this period. Oddly, most of the borrowing seems to be over by the point that, borrowing of new forms that have particular stress pattern seems to be, at least the massive influx is mostly over at this point. But especially given that people would have had knowledge of the multiple systems, it's definitely something worth considering. And I guess I would conceptualize that as saying something like, because of that knowledge, they have higher prior probabilities on learning some things relative to others. That would be one way to wrap it in. So maybe mistransmission in that system combined with it will give you most of what you want. So that would be kind of like what we actually did see. I guess my take-home message was just that purely by itself, which is often the way you see it discussed, mistransmission will give you a lot of unexpected and probably undesirable consequences. But combined with some prior knowledge, which hopefully would be able to make more specific about borrowing to represent, you can get a much more realistic picture.